In this video, we'll derive the sum of a geometric progression. Imagine we have a geometric progression with first term a and common ratio equal to r, so that the terms look like ar squared up to ar to the n minus 1. So I'm assuming that we have n terms. We can write the sum of the first n terms as a plus ar plus ar squared plus ar to the n minus 2 plus ar to the n minus 1. What I could do is write this sequence again underneath, and there is a method to this, and I could write it in reverse order. So ar to the n minus 1 plus ar to the n minus 2 plus ar to the n minus 3 plus ar plus a. So I've just written it in reverse order. Now, what I can then do is multiply my first sequence, or first series, by r. So I would have rsn is ar plus ar squared plus ar cubed, going up to ar to the n minus 1, and finally ar to the n. And then what I could do is subtract these two series. So I could do rsn, take away sn. And what we would notice is you would have ar cancelling out with ar. The ar squared, all of these terms would cancel out. Ar to the n minus 1 with ar to the n minus 1. But notice the Sn sequence, the Rsn sequence, has an ar to the n, which the Sn sequence does not have. And the Sn sequence, or series I should say, has an a, which again the Rsn is lacking. So I would be left with ar to the n, so all of these terms would cancel out effectively. I would be left with ar to the n, take away a. Now I can factorize the left-hand side, taking out a factor of Sn, giving me Sn multiplied by r minus 1. On the right-hand side, we could take out a factor of a, so we have r to the n, take away 1. And then we can divide both sides by r minus 1, giving me my sum of the first n terms as r to the n, take away 1, sorry, a times r to the n, take away 1, over r minus 1. You may also see this written as a times 1 minus r to the n over 1 minus r. And that is how we work out the sum of a finite geometric series. But notice if the modulus of r is less than 1, then the limit as n goes to infinity of r to the n is going to be 0. Because obviously if you have something like, say a half, if you take a half, if you square it, you will get 1 over 4, 1 quarter. Cube it, you get an eighth. Raise to the power of 4, you get a 16th, and so on. It becomes very, very small. If you raise 1/2 to a very large power, you will have a vanishingly small number. So the limit as n goes to infinity of r to the n is 0. So if we take the infinite sum, so if we take the limit as n goes to infinity of Sn, assuming that the modulus of r is less than 1, then we should get a times 1 minus naught, because the r to the n will approach naught, over 1 minus r, which leaves you with a over 1 minus r. And that is the sum to infinity of a geometric progression, as long as it converges, which occurs when the modulus of r, the common ratio, is less than 1.